Vika Academy. Today we want to look at limit points. If you have not subscribed to Vika Academy, kindly subscribe so that every time I post any video or tutorial, you are the first one to get notification. Share also with your friends so that every time I post an idea here, they will also get the knowledge. Okay, welcome. Today we want to look at limit points. Limit points is one of the main subtopic in real analysis. So you need to be very keen and get the difference and the definition and the meaning of limit points and its applications. Okay, let S be a subset of a linear set. A point P of the set is called a limit point, or accumulation point, or cluster point of S if every neighborhood of P contains at least one point in S which is not equal to P. So that's the key thing. So a limit point is also called accumulation point, and again is also called cluster point. So we say that this P is a cluster point or accumulation point or a limit point if the neighborhood of that P contains at least one point in S which is not P or which is not equal to P. So P is a limit point of S if every neighborhood N of P contains another point Q, say Q, which is not equal to P. Remember, this Q is also a member of S, such that if you take the intersection, you'll be able to get a set of P, but you'll find that it's not empty. Find it's not empty. So that means there's another element which is not actually in the neighborhood. It's not P. It's not equal to P. So the set of four accumulation points, or the cluster points, or limit point, is called derived set, and we note it by S with that bar up there. So let's look at an example. So if you look at this example here, you'll find that every member in this is actually a limit point or cluster point of this, and that will imply that zero one is a limit point for this subset. So if you look at this, you find it's not in this, it's not contained that. So that if you look at this, take some different look at the neighborhood, and you'll find that still it's not empty. And if you do this one again, checking the neighborhood of 1, you'll find that again it is not empty. And that will mean what? It will mean that it contains infinitely many points of 0, 1. So it contains many other points which are not 0 and 1, and therefore they are limit point. Okay, the set Z as which is the integer set, has no limit points at any given point P, because its neighborhood does not have at least one point of integer Z which is not equal to P. So it will not give you a point which is integer if you take a given point. So there is no neighborhood that will give you at least a point in Z which is not equal to P. That if you let P to be this, that is, let P be Z, a member of the integer set, and we check the neighborhoods of P. Of course, this is what we are calling epsilon, at least a small amount, a small value within the neighborhood. And if you justify this one, you'll find that whichever you get here is actually P. which implies that P is not the limit point of this, because we need to get another value of another element which is not P in the neighborhood. So the neighborhood here is still P. Again, if we let this P to be not in the integer, and we let it to be a member of a real set, and then you'll find that there exists a given integer such that it will lie in between that, so that if you do the intersection of that, you'll find that it is empty, and that clarifies that P is not a limit of Z. P is not a limit of point, a point of in Z. Let's look at a natural set. You'll find natural set if you take any limit again n point P, you find that its neighborhood will not have an extra another point except P, and therefore see that it does not have a limit point. Let's look at this set here. This set defined as this, where n is a member of natural set. You find in this case here, we will only find one limit point which is not a member of the S set is S, and you find that is 0. So if you look at this set here, take a given point P, you find that only because as n becomes larger, it tends to 0. So the limit here you'll find is 0, and is actually a limit because it is not in the neighborhood of this. It's the neighborhood of this, but it's not in really a member of S. It's not really a member of S. So for let positive epsilon, that's what you mean by epsilon, by what you call Archimedes principle. For a given epsilon, there exists n of the natural number, such that ne, there is n which depends in epsilon, which is greater than 1. So that's idea of Archimedean principle. So if this is true, then we will have to constitute something. So this will imply that this is true, which implies if you get some negative epsilon, we have that kind of interval, you find that it contains a point on S which other than 0. So 0 is a limit point of S, as you can see using Archimedean, and we need to show that 0 is the only limit point now of S, that is no point P in this. So can be a limit point of S as S is contained in this. So let 0 be not be equal to X, and X is a member of this. So this will be true because X is not 0, but it can be equal to 1 because this is closed up once and open down once. So by Archimedean, there exists a unique M in N such that this is true, so that if we get some variations in this, some small number, epsilon, you find that this here, it will contain no members of S other than X. Clearly you see that. This implies that X is a member of this, and it's not a limit point of S, and that means what? This 0 is the only limit point we have in this. It's the only limit point we have in S. Another example is that every real number is a limit point of either rational set or the irrational set or real set. So a limit number of real set, rational set, real set, and irrational set is actually real number. So the set, let's look at this set. This set given here is given here. You'll find this set here. It has two limit points. It has two limit points, and those limit points clearly you can see they are you look at this. These ones, you take these ones. So they go to 1 over n. Their limit tends to 0. Okay, so it's 1, 0. And if you look at the others, this one, you find it lies on that. So 1 is the limit point, and 0 and 1 are the two limit points that we have for that set. Okay, so kindly continue following this tutorial. I find that it's very interesting, and I told you this is key to data analysis. So you have to get every definition clear. If you have any question on this, kindly leave a comment there. Share also with your friends so that they are able to understand this concept. Let's look at this theory here. We state that finite sets have no limit points. We're saying finite sets have no limit points. So let's look at this. Let's talk about finite sets having no limit points. Okay, so consider the set A here, and we let this is a finite set, of course, and we let P be arbitrarily real number. We have a particular P. So then we let D1 be those values given that that definition. Then D1 is that, D2 is that, Dn is this, and we have R, which is minimums of the D1s. Then the neighborhood of this, which is given by P of P and R over 2, of course, contains no point. You find that that one contains no point in A since P is arbitrary. So you find that no point in A that's contained in the neighborhood. And that will imply that A has no limit point. A has no limit point. Okay, so kindly subscribe and share with your friends if you have not subscribed yet. Let's look at this theorem here. A real number set P is a limit point of some set S of real set if and only if, not that, every neighborhood of P contains infinite point of S. Okay, so a real number set P is a limit point of a subset S of real set if and only if every neighborhood of P contains infinite point of S. Let's prove this. Let P be a limit point of set S, because this is a if and if theorem. So let P be a limit point of set S. If that is true, then what happens? And we let N be a neighborhood of P. So you have to introduce that. So we need to show that N contains infinitely, or the neighborhood of P contains infinitely many points of S. Now, suppose to the contrary, N has finite number. So here we are trying to prove by contradiction. N has a finite number of points distinct. Say them. Say they are x1, x2 to xn. Suppose that is true. Then we have this from our previous theory, and R will be defined as that. Then the neighborhood of this we say has no element of S. And this now will become a contradiction to the fact that P is a limit point of S, because already I said that P is a limit point of S, and then every neighborhood of P contains infinitely many points of S. Infinitely many points of S. We have borrowed this from the previous theorem here, which says, and we had proven, finite sets have no limit points. So that if here we say that n has a finite number of points leading to this, then it will imply that this is true, this is true, this is true. Conversely, given that every neighborhood of P contains infinitely many points of S, it's obvious that every neighborhood of P contains a point in S other than P, and that point other than P is actually what makes P to become a limit point of S by definition of limit point, by definition of cluster point or accumulation point. Okay, so with that, kindly subscribe, leave a comment, ask a question where you have not really understood on the topic, share with your friends also. Bye for now.